Welcome to Balance of Economy. Before we dive into the data, please note that this is market research for educational and informational purposes only and does not constitute financial advice or a recommendation to buy or sell any asset. Let's look at the numbers.
So imagine trying to run, the most advanced artificial intelligence on the planet, this ethereal, cloud-based marvel that can write code and simulate reality, and suddenly it all just shuts down.
Right.
Not because of a cyber attack or some software bug, but literally because we ran out of a heavy orange rock that the ancient Romans used to make plumbing. I mean, that is the jarring reality of the 2026 economy.
It really flips your perspective, doesn't it? Because for this deep dive, we are tracking this massive hidden bottleneck in the global market. And if you are an investor or a tech professional or just someone paying attention right now, your eyes are probably glued to screens.
Oh, absolutely. Everyone's watching the screens.
Right. You're looking at silicon chips. You're looking at lines of code, generative AI models getting smarter by the week. But the stack of sources we have today from S&P Global, the Wells Fargo Investment Institute, UBS, the Bureau of Labor Statistics, they are all pointing in a completely different direction.
Yeah, they're screaming that the cloud actually starts deep in the ground.
Exactly.
And what's fascinating here is just the sheer irony of it all. I mean, the most sophisticated, frictionless technologies we're building are completely tethered to one of the most ancient, gritty, industrial realities on the planet. To build the future of software, you literally have to move mountains of dirt with massive diesel machines.
Okay, let's unpack this because the sheer scale of the demand side right now is, honestly, it's hard to wrap your head around. Let's look at the tech giants. So a few years ago, traditional enterprise data center used about 10 to 15 tons of copper for every megawatt.
Roughly, yeah, for every megawatt of installed power capacity.
Right. But S&P Global notes that today, if you look at a modern hyperscale AI data center, the ones built specifically for training these huge neural networks, that requirement jumps to somewhere between 25 and 33 tons of copper per megawatt.
It's massive.
I mean, the physical footprint has literally doubled in less than 5 years.
Right, and you have to visualize the mechanics behind that footprint. AI chips run incredibly hot, and they draw just massive amounts of electrical current. Like, take a single NVIDIA NVL72 server rack.
Okay.
Just one of those racks contains over 2 miles of internal copper cabling.
2 miles in one rack.
In a single rack, yeah. The backplane, the spine connecting all those processors, it is just a dense wall of metal. So when you scale that up, an entire modern AI campus being built out right now, you can require up to 50,000 tons of copper.
Wow.
We're not talking about pounds here. We're
Right.
talking about tons of metal just to keep the lights blinking.
I get the power requirement, but I have to play devil's advocate here for a second. If we are building the most advanced computing systems in human history, why on earth are we anchoring them to an industrial metal we've been using since the Bronze Age?
Right.
Why not just use fiber optics? I mean, it's made of glass, it transmits light, it's lighter, and we're always told it's the future of data transmission.
Well, it's a highly intuitive question, but it really just comes down to the brutal, unforgiving laws of physics. Yes, optical fiber is fantastic for long distances. It connects cities, it connects data centers across oceans.
Sure.
But when you are dealing with modern AI training, you have thousands of GPUs that need to act together as a single brain. And that requires ultra-low latency and incredibly high chip-to-chip bandwidth over, very short distances.
So the data has to move inches, not miles.
Exactly. And to use fiber optics over those tiny distances, you have to take the electrical signal from the chip, push it through a transceiver to convert it into a pulse of light, send it down the fiber, and then use another transceiver to convert it back to electricity for the next chip. That conversion takes fractions of a nanosecond. And more importantly, it requires extra power and generates extra heat.
And when you're doing that millions of times,
Billions of times a second, actually. When you're moving terabytes of data back and forth that fast, those nanoseconds and thermal loads bottleneck the entire system. Copper, on the other hand, is just raw, instantaneous conduction.
Yeah.
The electricity flows directly. So it is an absolute physical necessity for the latency requirements of artificial intelligence.
Okay, that makes total sense. You can't out-engineer physics. And big tech is clearly realizing that they are hitting a physical wall here. I mean, the capital expenditures for 2026 are astronomical.
Oh, they're staggering.
We're looking at Microsoft dropping $34.9 billion in a single quarter, almost entirely on infrastructure. Oracle is raising $50 billion for its Stargate project, and Amazon is spending $200 billion this year, mostly on expanding AWS.
And if we connect this to the bigger picture, It's not just how much money they're spending, but how they're spending it. Look at Amazon.
Uh,
They're actually bypassing the traditional supply chains entirely.
what do you mean by bypassing them?
Well, they recently signed a direct agreement to secure copper from Rio Tinto's Newton venture down at a mine in Arizona.
Wait, really? A digital logistics and software company is going straight to the mine?
Exactly. When a company like Amazon decides it needs to go straight to the mining companies, they are signaling to the market that they know raw materials, not code, are the true constraint here.
They are realizing the bottleneck isn't designing the chips, it's physically powering them. But here's the elephant in the room. The AI boom isn't happening in a vacuum, right? It is crashing head-on into an entirely separate, massive global shift.
Oh, yeah.
We are trying to electrify the entire planet at the exact same time.
Right, the energy transition multiplier. You basically have two historic megatrends trying to squeeze through a pipeline that wasn't built for either of them.
Exactly. Let's look at electric vehicles. The sources point out that a typical battery EV requires somewhere between 67 and 76 kilograms of copper. That is roughly 3 times the amount of copper you'd find in a traditional gas-powered car.
Right.
Now, the automakers aren't blind to this. The reports note they have been trying a process called thrifting.
Yeah, so thrifting is basically the engineering effort to use less of an expensive heavy material. Automakers have been trying to engineer the copper right out of the vehicle. For example, they've moved from using 10-micron copper battery foils down to 6-micron foils.
Which is tiny.
Incredibly good, yeah. Basically a fraction of the width of a human hair. And they're also trying to swap out copper bus bars for aluminum.
Wait, for the listener who might not be an automotive engineer, what exactly is a bus bar and why would they swap it?
Sure, so a bus bar isn't a traditional wire. It is a heavy, solid strip of metal that acts as the main spine, conducting massive electrical currents between the battery cells and the motor. Now, aluminum is cheaper and lighter than copper, which sounds great for a car.
Makes sense.
But aluminum is far less conductive. So to get the same flow of electricity, an aluminum bus bar has to be significantly thicker and larger. And inside an EV battery pack, physical space is at an absolute premium.
Wow, I see.
Quickly hit a wall where you simply can't thrift any more copper out without compromising the car's performance or its size.
And the data backs that up. Despite all those engineering tricks, total global copper consumption for vehicles is still surging simply because the sheer volume of EVs rolling off assembly lines is dwarfing the savings from those tiny micro adjustments.
Precisely.
But it gets bigger than cars. Let's talk about the grid itself. The International Energy Agency estimates that meeting global net zero emissions goals by 2050 requires over 400 million metric tons of copper.
And here is a mechanism from the reports that really stood out to me, because it impacts local communities everywhere. We constantly see press releases about making the power grid more resilient to storms, by moving overhead transmission lines underground.
Right, undergrounding.
Yeah. But moving a single mile of overhead line underground requires 10 to 40 times more copper than leaving it in the air.
Wait, why is such a massive difference? It's the same electricity traveling the exact same distance.
Because of heat dissipation. When a wire is strung up on a pole, the ambient air cools it down naturally. But when you bury that same cable deep underground, the soil acts as an insulator. It traps the heat generated by the electrical resistance.
Oh, wow.
If you used a standard wire, it would literally melt its own insulation. So to prevent that, engineers have to dramatically thicken the copper core to lower the electrical resistance and then heavily shield it. So every time a city votes to put their power lines underground, they are dropping a hidden copper bomb on the supply chain.
And it just keeps stacking. S&P Global points out that the average new U.S. single-family home uses about 439 pounds of copper. They note defense spending is highly inelastic, meaning, militaries will buy what they need regardless of price. And the emerging humanoid robotics sector alone will need 1 million tons of copper yearly by 2040. Add this all together, and S&P is projecting a 50% jump in global copper demand by 2040, reaching 42 million metric tons a year.
It is the electrification of everything, everywhere, all at once.
So we're stacking an AI boom on an EV boom on a grid rebuild. Let's look at basic economics here. If demand skyrockets, prices go up. When prices go up, mining companies see the profit margin, they buy some bulldozers, and they just dig more rock out of the ground to meet the demand. The invisible hand solves the problem.
I really wish it were that simple. This is where elegant macroeconomic models slam face first into the harsh physical realities of the rock face. In commodities, money cannot magically summon supply.
Right.
It takes an average of 17 years globally and up to 29 years here in the United States to permit, build, and operationalize a single new copper mine.
Let that sink in for a second. 29 years. That is longer than the gap between the Apollo moon landing and the release of the first iPhone.
Exactly. Copper supply does not respond to price signals the way a software product does. You can't just, hire more coders and push an update. It responds on a multi-decade delay. And the sources outline exactly why, detailing 3 distinct structural locks on the global supply chain.
Well, let's walk through those mechanisms because they are fascinating. The first major hurdle is purely geological. The Earth itself is fighting back.
Yes, the actual rock is degrading. Since 1990, the global average copper ore grade has plummeted by nearly 50%, falling from around 1.2% down to about 0.65% today.
Here's where it gets really interesting, and I want to offer an analogy for you listening, just to visualize what that percentage drop actually means in the real world. Imagine you are trying to sift tiny silver flakes out of a sandbox. In 1990, the sand was incredibly rich with silver. Today, the sand is depleted. To get the exact same handful of silver flakes, you now have to sift through nearly twice as much sand.
And to take your sand analogy into the industrial reality, imagine the massive trucks moving that sand run on thousands of gallons of diesel fuel. Imagine the washing process requires millions of gallons of fresh water, which is increasingly scarce.
Right.
Because the ore grade has dropped to 0.65%, miners today have to blast, haul, and crush 85% more rock just to produce the same single ton of refined metal they got 3 decades ago. You are spending significantly more energy and capital just to break even.
It's an industrial treadmill.
Exactly. And the mining industry is sprinting at full speed just to stand still.
Hmm.
Like Codelco, the massive state-owned mining company in Chile, is seeing their production drop precisely because their legacy mines are aging and the high-grade ore is simply gone.
Okay, so if the rock in the old mines is degrading, the logical step is to go find new, richer sandboxes. But the data shows the discovery curve is completely flatlining. Between 1990 and 2023, there were 239 major copper deposits discovered globally. Yeah. Only 14 of those were found in the last decade.
Which perfectly transitions us into the second lock, regulation. Let's say a company beats the geological odds, right? They find a massive, rich deposit of copper right here in the United States.
Okay.
They can't just start digging. They enter a labyrinth. The National Environmental Policy Act, or NEPA, requires an environmental review process that routinely runs for over a decade. It involves layers of overlapping state and federal agencies, water rights disputes, and complex land swaps.
The reports highlight a massive, agonizing case study on this, the Resolution Mine in Arizona. The deposit was discovered all the way back in 1995. It is incredibly rich. If permitted, this single underground mine could supply an estimated 25% of total current U.S. copper demand.
It's huge.
But the sources note the ore sits deep beneath Oak Flat, an area considered sacred by the San Carlos Apache tribe. So the project has been locked in a bitter dispute.
All right, so instead of producing metal, the project has been locked in this 3-decade web of environmental litigation and tribal land disputes. In fact, the final environmental impact statement was fully rescinded by the government in 2021. Look at the raw numbers on that project. Over 30 years and $2 billion of capital have been spent, and as of 2026, not a single ounce of commercial copper has been produced.
Wow. And what does that do to the market as a whole?
It causes total capital flight. A mining executive is going to look at a 29-year, multi-billion-dollar legal war of attrition in the U.S. and say no thanks. They take that investment capital to Chile or Peru or the Democratic Republic of Congo, where they can navigate the system and have a mine flowing in a fraction of the time.
Which, ironically, leaves the United States completely reliant on foreign supply chains, importing half of its copper needs every year just to hit its own green energy goals. Okay, so geology is failing us, and regulation has gridlocked domestic production. What about the third lock? Every time I talk about resource scarcity, someone brings up recycling. Can't we just recycle all the old e-waste, strip the wiring out of old buildings, and melt it down?
This raises an important point, and it is exactly where a lot of optimistic economic models get tripped up by reality. Yes, copper is infinitely recyclable without losing its conductive properties. But the global end-of-life recycling rate is currently only about 45%. More than half of it ends up in landfills or is just lost in processing. But the true fatal flaw in the recycling argument is the time lag.
Explain the time lag, because the math here is wild.
Well, when you put copper into a building's wiring network or bury it in a municipal power grid, it stays there for 40 to 60 years. It doesn't come back to the scrapyard quickly, like an aluminum soda can.
Which means the scrap metal that is hitting the recycling facilities today, in 2026.
Is the copper that was installed in the 1970s and 1980s. And if you look at historical data, the total global volume of copper consumption in 1980 was a tiny fraction of what we consume today.
Right, there were no EVs.
Exactly. You simply cannot feed the massive multi-million-ton demand wave of 2026 AI data centers and modern EV fleets with the scrapped electrical wire from a demolished 1985 office building. The arithmetic is physically impossible. The millions of tons of copper we used to build the consumer electronics boom of the 2010s, that won't be available for recycling until the 2040s or 2050s.
So we have established an irresistible force, the tech giants and the energy transition slamming into an immovable object constructed of degrading geology, regulatory paralysis, and a massive recycling lag. Let's bring this to the immediate market fallout right now in 2026. The sources are increasingly referring to copper as red gold.
It has absolutely become a smart money favorite. We're looking at a report from the Wells Fargo Investment Institute, and they explicitly tell their clients that industrial metals are a highly attractive, ancillary way to play the AI investment theme. Yeah, they're looking at these exact supply locks and projecting that copper demand will vastly outpace mine supply growth, leading to a staggering global deficit of roughly 30% by 2035.
Let's contextualize what a 30% deficit actually means in the real world. It doesn't just mean the metal is more expensive. It means that for every 10 miles of power grid a country wants to build, or every 10 AI data centers a tech giant plans to open, 3 of them simply will not have the physical material to exist. It is a physical hard stop on economic growth.
And we are already seeing the squeeze. UBS is forecasting a copper deficit exceeding 400,000 tons just for this current year. And if you want to see the immediate pain, look at the Bureau of Labor Statistics. In February 2026, the Producer Price Index, the PPI for copper wire and cable, hit a massive 22.4% year-over-year increase.
Just in 1 year.
In 1 year. That is the wholesale cost. That is the exact wire going into every new neighborhood substation and every Amazon server farm.
This brings up a critical point about market positioning. Because supply is so constrained, the companies that actually hold viable, proven resources in the ground are becoming incredibly strategic assets. The reports heavily mention a company called Doubleview Gold Corp, operating the HAT project up in the Golden Triangle of British Columbia.
Right. They recently reported an updated resource estimate of over 600 million tons of what the industry calls measured and indicated resources.
Let's clarify that term for you listening. Measured and indicated isn't a geological guess. It means a mining company has actually spent years out in the field drilling core samples out of the rock, analyzing them in a lab, and mathematically proving that the deposit exists with a high degree of confidence.
Exactly.
Doubleview's numbers outline over 5.8 billion pounds of copper equivalent in that category alone, which bundles the value of the actual copper plus the gold, cobalt, and silver found in the same rock.
And what makes a project like Doubleview's HAT project so vital right now is the geography. It is in British Columbia, Canada. Remember the regulatory nightmare we discussed with the U.S. Resolution mine?
Yeah.
When the United States is forced to import half its copper, and domestic permitting takes 29 years, a massive proven deposit sitting just across the border in a safe, mining-friendly North American jurisdiction becomes geopolitically critical. When the global market finally prices in true structural scarcity, the projects that have already done the decades of grueling groundwork hold all the leverage.
But let me push back on the panic for a second, because one of our deep dive sources features a ground-level anecdote that really resonated with me. There's a guy named Mark, an electrical contractor operating out of Phoenix. He's been working on residential builds and commercial grids for decades.
Okay.
And Mark pushes back hard on this whole generational supercycle narrative. He says, listen, copper prices have always been volatile. They go up, the builders panic, then they go down, and the market normalizes. Why isn't Mark right this time?
It's a brilliant pushback, actually, because Mark is entirely right about the history of the commodity. Copper has always been a boom and bust cycle. But Mark is missing the shift in the underlying mechanics here. Past cycles were purely cyclical.
Meaning what?
Meaning, when prices spiked in the 1990s or 2000s, it incentivized miners to quickly expand operations at high-grade mines, and new supply hit the market within a few years, cooling the price back down.
Ah, so the invisible hand worked.
Exactly. But today, the locks are structural. Higher prices today do not change the fact that the global ore grade has collapsed. A higher price tag does not magically bypass a 10-year NEPA environmental review. Electrification of the economy, announcing a sweeping new EV mandate or breaking ground on an AI campus that happens in a matter of months.
Right.
But extracting the copper to build that infrastructure takes decades. You can log online and order 1,000 servers from NVIDIA today, but you cannot summon the metal from the earth on demand.
So what does this all mean for the listener tracking these markets?
It means we are facing a profound timeline mismatch that changes how you should read every piece of tech news. Every time you see a headline about a trillion-dollar AI infrastructure announcement or a new citywide green energy grid, you have to ask the unspoken question, where exactly is the metal coming from?
Because if the math doesn't work, the cloud doesn't run.
Precisely. And this leads to a scenario that current economic models haven't fully priced in yet. If land-based mining takes 30 years, if the ore quality is dying, and if the AI computing race is viewed by superpowers as a matter of national security, how far will humanity go to secure this metal? It is highly probable that this physical bottleneck will force the world into the incredibly controversial realm of deep-sea mining.
Wait, mining the ocean floor?
Yes. The bottom of the Pacific Ocean is scattered with polymetallic nodules. These are like potato-sized rocks sitting right on the seafloor that are unbelievably rich in high-grade copper, cobalt, and nickel. Right now, touching them is an absolute environmental taboo.
I can imagine.
But think about the pressure cooker of 2026. When the AI servers start browning out and the electrical grid can't handle the load of the EV transition, the geopolitical pressure to drop machines to the bottom of the ocean is going to be immense. The dark, freezing depths of the sea could very well become the next great global battleground, simply to keep our data centers running.
That's the data for today. Now, I want to hear from you. Can the AI revolution survive a copper shortage, or are we hitting a physical wall? Drop your thoughts in the comments below. Don't forget to subscribe to Balance of Economy for high-density market insights. Stay sharp and stay informed.